Alright, so in this next equation, or in this next question, we are told that a hospital purchases a new MRI machine for $500,000. The depreciated value after t years is given by the equation y equals 500,000 minus 40,000 t, and our parameters are that t is greater than or equal to 0, but less than or equal to 8. And they ask us to sketch the graph of the equation. So I just want to point out here that this is a linear function. We have an equation that's in terms of y equals mx plus b. It looks a little strange because we're not used to seeing a linear equation with things other than x in it. But in this case, our t is acting as our x. It's just another variable that's used to represent an amount of time passed measured by years. The other thing is, usually you would see this term written before the 500,000, but that's not the case here. That doesn't change how you would solve it though. So first we're just going to make a table and plug in some points, and with those points we're just going to maybe plot 2 or 3, and from there we can sketch a pretty accurate graph of the equation. So the simplest point to plug in at this point for x, which I'll rewrite as t just for simplicity's sake. The simplest point we can plug in right now for t is 0. Then that would give us our y-intercept, if you recall what the definition of the y-intercept is. So at t equals 0, we have y equals 500,000 minus 40,000, and this is going to go off the thing here, so I'll just rewrite it. So to repeat, we have 500,000 minus 40,000 times 0. Well, 40,000 times 0 is just 0, and we're left with y equals 500,000. So right here we have just 500,000. I'm just going to write this as 500k to simplify the writing process. Now let's go after 1 year. So basically what this means is at 0 years, it's like it's brand new, they've just bought it. So let's go maybe 1 year after they buy it, then what would the cost, or then what would the value of it be? We would have y equals 500,000 minus 40,000 times 1. 40,000 times 1 is just 40,000, so we have 500,000 minus 400,000, which is just going to give us 460,000. And I'm just going to write this as 460k. Then let's see what the value would be after 2 years. So we're going to have y equals, excuse me, 500,000 minus 40,000 times 2. 40,000 times 2 is just 80,000, so we're left with 500,000 minus 80,000, which is 420,000. And I'm just going to write this as 420k. Okay, so now we can go and graph, or we can sketch the graph of this equation now that we have a couple points plugged in. So here we have the graph, and on the x-axis we have the time, so this is t in years, this being 0, 1, 2, 3, 4, and so on. On the y-axis, we have the value of the MRI machine. So it starts at 420,000 and goes up by 20,000 each peg. So at 0 years, our value is 500,000. So right here at 0, we go all the way up to 400,000, 500,000. We draw a circle. Then we at t equals 1, we go up to 460,000. So we go here. And at t equals 2, we go to 420,000. And then when we go to sketch the graph of this equation, we can see it goes something like that. This would go on. This would go on until it gets to 8. But you can see that it's a negative sloping linear graph, which makes sense with what we're given, because this term here has a negative in front of it, and this is really like our m and x over here if we're talking about a linear function. Our m is negative 40,000, meaning it's going to slope downwards, and we can see that indeed it does slope downwards. Alright, so this next problem is a two-parter, and it's kind of one of those more abstract type of problems. It says, find a and b if the graph of y equals ax squared plus bx cubed is symmetric with respect to the y-axis in the first part, and in the second part, the origin. So when I'm taking a look at this first part, let's break it down with the first part. So we're just looking at what a and b must be if the graph of this equation is symmetric with the y-axis. So what I'm thinking is that if it's symmetric with the y-axis, I want to get this equation into a form that just has ax squared in it. Because if it has plus anything over here, it will be shifted. It will be shifted or translated in some way or another. And if there's an x cubed in it, it's going to turn it into a cubic function, which we don't want at all. So we want this thing to be 0, and this thing to just have x squared in it. A can be any number. It can be 7x squared for all I care. I just want it to be x squared. I just want that in there. So if I'm going for the simplest answer, I would put 1 for a, because 1 times x squared is just x squared. You could put 2 or 3 or whatever number, any real number basically, for x squared. And if I want this to evaluate to 0, one of these has to be 0. And if the only thing I'm changing is b, I would make b 0. So in part 1, I would say a is equal to 1 and b is equal to 0. Now if I'm looking at the graph of an equation that's symmetric about the origin, it's going to look something like this. It's going to look like a cubic function, or at least I know cubic functions are symmetric about the origin. So knowing that, I just want this x cubed in here, and I want this ax squared to evaluate to 0. So once again, b could be anything. It could be 3 or 17 or 55 or 100 million. But to keep it simple, I'm just going to say b is equal to 1, so that 1 times x cubed is just x cubed, and a, I want it to evaluate to 0, because if I have this x squared in here, it's going to change this in a way that is going to make it no longer symmetric about the origin. So in order to get this equal to 0, and the only thing I can change is a, I would have to say a is equal to 0, and b is equal to 1. But again, in the second part of the problem, b can be any number, and in the first part of the problem, a can be any number.